Welcome to Study Loop.
We're taking 3.5 moles of a gas that has a molar specific heat of 5/2 R at constant volume. It's at atmospheric pressure, which is 101 kilopascals, and at an initial temperature, 255 Kelvin. We want to add to this gas 175 kilojoules of heat in 3 different ways. One is through an isothermal process. Another is through an isochoric or a constant volume process. And the other one is through an isobaric process. And we want to know what is the work done by the gas and what is the final temperature of the gas. Always remember, work done by the gas is just minus work done on the gas. All right. In an isothermal process, well, we could go for the work done being minus nRT with an ln of the 2 different volumes, or since there's no change in thermal energy, and thermal energy is Q plus W, we can have Q equals minus W. But this W in this case is work done on the gas. So it's just equivalent to the work done by the gas, which is 1.75 kilojoules. The final temperature, it's isothermal, so the temperature has not changed. 255 Kelvin. In a process under constant volume, since the volume doesn't change, there is never any work done on or by the gas. 0. The final temperature, on the other hand, we're going to need to use our molar specific heat. And CV delta T. Plug in what we know and solve for what we want to know, the change in temperature, right? N is just number of moles, CV is 5/2 R, and R is 8.31 joules per mole Kelvin. Plug that in, and you will find that your temperature is going to change by about 24 degrees Kelvin, 24.067. But we've got 3 significant figures here, so add that 24 to your 255, and you'll get about 279 Kelvin for your final temperature. Let's move to the isobaric process. We can do the change in temperature the same way, except we need a constant pressure molar specific heat now. But that's just taking the constant volume one and adding another factor of R. So in this case, we have 7/2 R for that. Again, we'll plug some stuff in. 7/2 R for CP, 3.5 here, 1.75 kilojoules, so times 10 to the 3. We'll get a change in temperature, and we'll add that to our original temperature, and we'll find that our final temperature is about 272 Kelvin. Now, how are we going to get the work done when we don't have 2 volumes, right? We're used to work being negative P and then the change in volume. Well, how about this? How about CV is normalized by the number of moles, the change in thermal energy divided by the change in temperature. And in this case, our CV is 5/2 R. Why are we solving for this? Well, because a change in thermal energy is work done on the gas plus heat given. So if we find the change in thermal energy and we subtract the heat that we're giving to the system from that, we'll get the work done on the gas, pop a negative sign on it, and we've got the work done by the gas. When you solve for the change in thermal energy, you're going to get a rather large number. You're going to get something about like 1250 or 1249.928, something around that. We can subtract our 1.75 times 10 to the 3 and throw a negative sign in front of the whole thing, And we'll get the work done by the gas in the isobar is about 500 joules.